Okay, with this video we come to the end of a chapter on angular velocity, angular acceleration, how to equate angular rotation with velocity of, say, if there were a rope coming off of a pulley. And the section right before this video in the book that I'm relating these videos to, Young and Freedman's University Physics, the section right before 9.5 was on the kinetic energy of a rotating body. And that unit on a rotating body, the kinetic energy, we talked about a term called the moment of inertia. It's not a very helpful term. Rotational inertia, maybe that helps a little, but it's basically, it has to do with the kinetic energy. I like to call it the potential kinetic energy of a particular circular a mass that's going to rotate. Its mass, its radius, kind of, there's a potential energy. I know this is not the right one. This is not the right way to call it, but there's a kind of potential energy to a mass that you're going to spin, and that's something like what they call officially the moment of inertia. The parallel axis theorem. What is the parallel axis theorem? It's really the last thing you really need to know from this chapter. Parallel axis theorem has a lot of power because what it does is it allows you to figure out the moment of inertia if you switch the axis that something's rotating on from the center of mass, because pretty much the previous sections have assumed that you were sticking the thing the axle you were rotating something on through the center of mass of whatever the object was. What happens if you shift the thing you're rotating from its center of mass? How does that change? Well, there's a nice little formula. And if you want to read any physics book like Young and Freedman's University Physics, they'll derive this formula for you. But to find the moment of inertia for a point that is not in the center of mass, drum roll please, here's the formula. So the moment of inertia through a point that is parallel, and by parallel it means parallel in the z-axis, so parallel coming out of the body. That wasn't immediately clear to me. But parallel to the center of mass, CM, ICM, the moment of inertia through the center of mass, if you're going to parallel, P for parallel, move the axis over a certain amount, let's call it D. So how do you calculate the moment of inertia for a different axis than the one going through the center of mass? Well, you're going to take the moment of inertia going through the center of mass, and you're going to add to it the mass times the distance from the center of mass squared. And there you have it. Nice little formula. Now, again, if you want to know how to derive it, if you want to know why that makes sense, pick any physics book and read that section, or Young and Freedman, since I'm so happily using that book. I'm sure they'd love for you to read it from their book. But that's the thing I think you need to know about the rest of this chapter. But there is another section, and this section is basically, where do all these moment of inertia equations come from? It's a asterisked section, which means it involves calculus. It involves integral calculus in particular. Calculus seems hard. It's not as hard as people make it out to be. See the videos that I've done. But anyway, where did these moment of inertia equations come from? Remember that the moment of inertia is a kind of shorthand for the parenthetical part in this equation. So the rotational kinetic energy is 1/2 mr squared times the angular velocity squared, and that mr squared part in the middle is what they call the moment of inertia. It involves the mass of the body, it involves the radius of the body. But what happens if you have a solid kind of body of some kind? And if you remember, near the end of the previous video, I went through all the different equations for like a dowel, a kind of cylindrical piece of wood or something, or a plank, or a sphere, or a cylinder. And Young and Freedman give you the formulas for all of those. Well, guess what? In this chapter, it derives almost all but two of all those formulas. They provide the justification for it in this chapter, in this section, in the examples. mr squared. Now what is mr squared? For a solid, it is the integral of r squared dm. Again, if you don't know calculus, let me just give you a taste of it here. dm has to do with kind of a infinitesimal slice, as it were, of mass. Integral means you're going to add up all of those little infinitesimal slices of mass. You're going to do it for a particular radius, and then you're going to do it for another radius, and then you're going to do it for another radius, and so the integral adds up all those infinite little teeny radiuses times the little slice of masses, and that's going to give you the moment of inertia for, say, a sphere or a cylinder or whatever, by adding up all those. So it gets a little complicated. You don't really need to know this necessarily. Now you might, if your professor's mean, or if you want to do advanced physics, but it's just basically explaining where those formulas came from. So if the integral of r squared dm is what the moment of inertia is technically for a solid body, you have to, in integral calculus, if you're going to integrate, you need to have similar terms. So r, radius, is a matter of space. So the dm, the differential of mass, is not in space. It's in a mass quantity. So this is often what calculus involves little clever little switcheroos. And what they do here is they build off the fact that density, this is a Greek letter rho, is the dm dv, the change, the infinitesimal change in mass per infinitesimal change in volume. And so by substitution, what we have is that the moment of inertia, just taking the previous equation and substituting this for dm, you get, and the assumption here is that the density is uniform. With integrals, you can factor out a constant. So assuming that the density of whatever object you're talking about is constant, then rho becomes a constant, and you can pull it out. Rho, and then dv is a spatial quantity. It's a volume. So r, radius, is a space quantity, and v, volume, is a space quantity. Okay, now we're ready. Assuming the density is constant. So then what the next three examples do in this last section of the chapter is it derives all but two of the moment of inertia formulae that are on page 299 in Young and Freedman's 12th edition using integration. But I don't want to bore you with those. Email me if you want an explanation. And there you have this chapter, Chapter 9, on angular velocity, acceleration, kinetic energy, and so forth. To close out this video, there are all of the formulas that were given in the previous video on page 299, that in the three examples at the end of Chapter 9, he derives all these showing using integral calculus. So, there you have it, the end of Chapter 9.